I hope a friendly way. That is, I'm going to try and avoid as much as possible too many formulas, and rather do some simulations to show you things as I go along about mixture models. I don't think we have an agenda of any kind, and I just wanted to, I feel I can tell you some things that might be useful. And I'll show some scientific and simulation examples to start with, and some definitions. And then I'll talk a little bit about what can be gained by using these mixture models. And then at the end, I'll talk about the reason that mixtures are ubiquitous from a technical, mathematical point of view. So this is the simplest possible mixture model that you could think of, is to say I have a coin, I flip it, if it comes up heads, I choose a normal with mean -1 and variance 1, and if it comes up tails, I choose a normal with mean 1 and variance 1. So that's the sort of banal mixture model situation. It's the simplest possible. There are two components in the mixture, and that's what it is. Now, some people get confused because they think that if you take two normals and sum them, that might make a mixture, and that's not a mixture, right? So if I take y, which is, say, x1 and x2, and they have those two, that's going to actually also be a normal, and it's not a mixture distribution. So that, just to say, that's more a convolution, and this is a mixture. All right, so let's just do some examples and hope that the examples will come up. All right, it's all right. Here they are. So some practical examples, and I did some code. It's sort of, I wrote this especially for this, so there are probably some bugs in it. So this is. So a simple Gaussian mixture of two components, and I'm going to do again the fair coin flip, for instance, and then you generate a random number according to that component, and here I have one with mean 1 and the other has mean 2, and they have different variances. So if I wanted to do that with the computer, and I think that looking at the algorithm or the pseudocode is kind of useful, and then you get used to what the pseudocode in R looks like. Here I flip a coin by taking random uniforms and looking as if they were bigger than a half. Then I look at a table of coin flicks. The one I got here was 504 versus 496. And then for the zeros, I'm going to generate the first normal, and for the ones, I'm going to generate the second ones. And the important thing is what you get at the end. So this is sort of the standard histogram that we'd make. It's a little bit ugly. I made more classes here. It's still pretty ugly. This is better in some sense. So this is the final distribution. This is what you would have observed if you were a statistician and that was your data. What I gave you before is the probability model, which we often call the generative model, that made that data. And usually we don't know that. We're statisticians, so we see this and we say, what made the data? What are the components? And so on. So this is, and if you look at what we know, which is hidden to a statistician, is this. And so we have these two distributions with some amount of overlap. In fact, there are three histograms. There's the two, there's a blue one, there's a pink one, and the overlap one is supposed to be purple. I'm sorry, it's kind of at the back. But what you see is when you do the overall distribution, the overlap is going to sum. And so if you have the distributions where you have the mixtures are not very separate, what you'll see is a wider histogram with a small bump in the middle, and at the limit you'll just get a kind of really flat distribution which looks like that. And when you look at histograms in general, you don't have a good idea about the components. So it's sort of, that's what's it. So that's what a simple mixture of two components is. Let's do something where you could wrap it into a function. That's what it would look. You could have more than two groups. So you might, have groups which are sort of, if you're lucky, they have small variances and you'd see waves. So if you had 3 modes like that, you'd say that you had 3 different populations, and you could generate multiple normals. And then the other thing that occurs that we see a lot of, instead of just measuring one thing, and many people do clustering, and that's because that's where the mixture comes in, that you see this. If you were in high dimensions and you saw data like this, maybe, you see it, and in fact you say they cluster, and a statistician says there's a mixture. That is, there are 3 component distributions, and they might have different variance covariance matrices, and it's a mixture of these 3 components. So nice and separate modes, and you have these clusters. So that means that you could explain having the 3. You could do any kind of clustering and you'd see that. So that's for the multivariate normals. And there are lots of methods for finding the components in mixtures, and I'm not going to talk about the EM algorithm, which specializes in labeling those kinds of mixtures, but that's a good one. Now I'm going to talk about what we really do in biology, and this is a paper that appeared almost 10 years ago, where we were looking at microarray data, and there were types of data which occur a lot, which are not at all, you don't see 2 or 3 components, you just see an overall distribution that just doesn't look normal at all. And this distribution is in fact a mixture in the sense of thinking about generating numbers from the same family in some sense, in the same families, I'd say, and having a way of generating the components. So I think it's helpful if you think about the normal. I said heads you did N1 and tails you did N2. It might be better to think about it more. You have a box in which you have half of the parameters are mu1, sigma 1, and the other half of the parameters are mu2, sigma 2, and you're going to draw with replacement in that box the values of your parameter, but it's a normal. Okay, so that's just a little step away. And here we do the same thing, but in fact, instead of having only 2 possible values, we're going to actually have a continuum of possible values for the parameters. And we have fixed parameters, so there's just scale parameters, thinking of theta, mu, and sigma are examples of them. And then you generate a normal and also an exponential, and you generate random variables which are like that. Now, once you've chosen Wi, so you have this model in which you have a normal and you generate Wi, and then you're going to generate the Wi is from an exponential 1, and then you'll generate a normal with those as the parameters. So it'll be normal here, for instance, theta plus mu Wi, and then the variance also, depends on, and so the variance is square plus so that's going to be I, there we are. So you generate something from here, and you look at that distribution. Yes?
Just to clarify.
Yes.
Here, theta, mu, and sigma are some values that we've chosen.
Yeah. Given to me by God, right.
Yeah. But why would you use that formula?
Sorry, I'm doing a generative model. I just want to show you what the data looks like.
So we've happened to have just chosen this.
I chose this because I know upstream, right? Sorry, it's not.
Yeah. So we've
I wanted to do the generative model first.
This is an example of a.
This is an example of a hierarchical model, in some sense.
We could have, for some other reason, we might have chosen a different.
Absolutely. No, this is just one example. I'm going to do tons of examples, but the idea is there are levels. And in some sense, you could say that above, from here, is the theta, sigma, and mu. They were given, but I could go up, but I'm not going to. Is that okay? I just want to show you what the data look like. This is a realistic mixture. And so it's a complex mixture of normals. So I fixed theta, mu, and sigma to some values. And then I generate 10,000 exponentials with mean 1. And then I generate normals with that W. So these are generated from exponentials. Okay. So exponential 1. I get the WIs, and then I generate the normals. So that's my algorithm. And this is the histogram of what you get. Here's slightly better histogram. So it's definitely the case that even the histogram tells you this is not normal data. So, but it's not a discrete number, a small number of components like we had here. And this is actually the most common case is you generate these by a random process so that you have many, many values for your parameters.
Is this like instead of having two components, which we
Yes.
started with, here you've actually got an infinite number?
Yeah, that's right. I had an infinite number, and that's the most common. Now, it turns out that often when you do an infinite number of components, when you look at this actually has a name. This is the Laplace distribution. It's Laplace's distribution of errors. It's an asymmetric distribution with the three parameters that I called. And the reason I wanted to use it as an example is because in all our discussions, we've been saying, should we know the components of the mixture of what we're doing? Should we be able to label? So when you're doing a very small number of things, in order to conclude, you sort of have to label them, and you have to know the components. In this situation, actually, we get a marginal, in some sense, a distribution here from which we can get all the information we need. And this information, for instance, how do you measure the central location of this distribution? Laplace already showed that the best way of doing this is to take the median and not take the mean. And the mean absolute deviation is much better for looking at variability than looking at the variance. So it tells us a lot about what we should be doing. And actually, we made this discovery about microarrays after the fact that Terry Speed and Sandrine Dudois and several people had said, never use the mean on microarrays, always use the medians. And this justifies the reason why. But they had found it heuristically, and this is the theoretical justification, because this is actually the error. And I'll show you some more plots and ways of using it. So the variance in the mean in this model here, we write it out. You see the expected value is theta plus mu, and the variance is sigma squared plus mu squared. And I also wanted to talk about this example because it's slightly more interesting than the Poisson, but it has the same feature, which you see throughout your data, all of you. And that is that the means and the variances are linked. So as as you get to higher values, higher abundances, the variance changes with the average that you're at. Now, depending on whether you're doing proportions or whether you're doing counts, the variances change in a different direction, but you have this dependency of the mean and the variances. So this is a feature, and it's very important, and you have to leverage it, but you have to take it into account. And so that's what we did also for the Poisson gamma mixture. That's a different mixture. So let's talk about the Poisson gamma, because it's used a lot in ecology and also for different evolutionary rates. It's used for evolutionary rates on the tree, and in Bayesian statistics and for abundance data, it's very popular. So just to say, remind you about the Poisson, this is a Poisson variable with lambda equals to 2. So I'm not going to write out the formula for the Poisson, but this is, you get a majority at the value 2, but you also get a lot of 1s and quite a few zeros. You get 3, 4, 5, 6, and then it hardly goes to 7. Okay, so that's a typical Poisson random variable. And what we're going to do is we're going to also do what I just did. I'm going to generate. So we have, if you have a Poisson random variable, we're going to generate at random the parameter of the Poisson. So we'll do that from a gamma distribution. And then from there we get, I think I called them lambdas. Not quite sure. Lambda I, say. You generate one, and then you're going to generate something according to a Poisson. Lambda I. But you could do that as many times as you wanted observations. And so that's where this method, it won't show you so much clumping as a variability which is observation dependent. All right. So this is what it looks like, the gamma distribution that we used here with a shape parameter of 2 and a scale of 3. And so we're going to combine that. And suppose I wanted to generate, I'm going to have 90 different Poissons. And so I'm going to generate my 90 parameters from this gamma distribution. So I just do it there. It's written lambdas equals R gamma, the number I want, so 90, and the shape and the scale parameters. And then I'm going to generate 90 Poissons, each one from a different. So they each have a different parameter. And now I'm going to sort of do a statistical verification of the fact that I said that when you do a gamma Poisson mixture, in fact, your marginal, again, it's a distribution that we already know how to study. So we don't have to go back to the components of the mixture in order to know a lot about how this varies. And this is sort of interesting. So does it have a negative binomial? You can look at if you fit it, I fit that distribution to a negative binomial, and then I made what's called a rootogram. And so what a rootogram is, when we look at whether a continuous variable fits a model, we often use QQ plots. But when you are doing discrete distributions, the QQ plot can never come out as a straight line, or it has steps in it. So what we like to do is we make a rootogram which has the theoretical values in red here, and then the observed values are the length of these triangles. So if you had a perfect fit, every rectangle should end on the horizontal axis here. So you see here it doesn't fit perfectly, and there, but we can make a goodness of fit test using the chi-square as well. But this is just a visual way of doing it. So you can see it fits pretty well, actually.
These were actually generated from your Poisson gamma mixture.
Yeah.
And then you're saying, okay, I generated these from a Poisson gamma mixture, but let's pretend I did. As the statistician, you don't know how these data were generated.
Yes,
in
that's
reality.
right.
And you're saying, well, I don't know that because
Yeah.
nature's done this.
Yeah.
And me as a statistician, I think, oh, that could be a negative binomial, which is a different distribution.
That's right. That's right.
Would
And
it-
but when you see it, you see if you know some things. So if you see a negative binomial, you think, haha, I have a mixture. I know what mixture it is. And if you see a Laplace, you say, I have this mixture of normals. And so there are many distributions which actually, in the back, there's an explanation in terms of mixtures. Now, there's a theoretical reason why that's true, in that the observations are not necessarily IID, but they might be exchangeables. That's why most of the time you do have a mixture. But I wanted to stress this point about the fact that we can use this, and what we're doing is really we're borrowing strength across many of the instances. They don't have the same distribution, but we can go back and use the overall distribution here to go back and say, oh, it came from a gamma. So we're borrowing strength to go back to the generative model. Yeah.
I mean, isn't it the case also that sometimes the decomposition into these mixtures is non-unique? So
Yes, there's an identifiability problem sometimes, right? So if you leave enough, yes, but then you have to add a constraint. So or you have to say it has to be parsimonious. That's true. That's true. It's not identifiable, but usually.
Laplace is identifiable.
What?
A Laplace if something comes from a Laplace distribution, it has to be a specific mix of normals. Is that true?
Yes, you can write it down.
So if it's a negative binomial, it has to be.
But it's not. I mean, it's an infinite mixture, right? So it's generated by lots and lots and lots. But it doesn't matter. It doesn't matter. The thing is, you don't have to get. You don't have to get upset that you didn't get the individual components.
Yeah.
Right.
So you can still work with this, what
Yes.
we statisticians call a marginal
Right.
distribution.
Yes.
And you say, well, that's just the distribution from which these things come.
Right. Right.
And in a sense, they come from that independently.
Right.
If you think of it in that way. So this is just to clarify,
Yes.
or maybe you could clarify this. How does this relate to a mixture of, different microbial populations, for example? So out there in reality, we've got a bunch of different populations. They might be microbial. Or something. Is this somehow connected with that, or is that a different problem?
Well, so
Maybe you come on to that later.
no. We had this discussion because it is related in that sense over there that you could have, because and you're asking how many clusters are there, and but it is much more general than that. So the reason in microbial populations that you might have different variances, it's not only the biology, it's also the technology. And the instances, the number of reads and things like that. So all of that adds to the mixture, right? It's not just, so if you're just doing composition data and say, well, these groups have different covariances and things like that, then that's different.
But
Yes.
so there is a sense in which the analogy is a bit stronger than that, I think, which is you can say that the organism is the central middle step in the mixture. So you can say, if I have this organism, then I have a probability of observing this read.
Yes.
Okay.
Yes.
So you can say it's like the intermediate distribution. So
Yes.
so
Which is conditional.
yeah.
Conditional,
So,
given
so
that
this
you're
is
in.
there's a mixed organism in there. Given that the particular organism that this read comes from is this, then the chance that the read is
Yes.
of a particular type is something else. So that is
Yes.
a mixture distribution.
Yes. But there's I didn't want to confuse people, and that's why I kept away mostly from the multinomial Dirichlet, because people often think that the only way of doing mixtures is through composition data, which isn't the truth.
Okay.
So that's why I didn't want to.
Okay,
It's
but
more
yeah,
these hierarchical types of, yeah,
okay, but that is the sense in which I meant it.
right.
So-
Okay, we agree. So this is just about the math and how writing out that it actually is the gamma mixture of Poisson and the binomial. Another mixture which is used nicely in applications, and Penny's not there, but that's why I thought she might be interested in this one, is that our model, which is often used for PCR error, is a gamma exponential noise model. So you generate the parameter of the exponential with a gamma. And that's just because really you have this multiplicative process, I guess, and that's where the error structure works well, and so there's a link to that paper. There have been some nice applications. Yes?
The gamma exponential, does that have a marginal?
That has a nice marginal. No, well, they're the same family, so it's a gamma. Yeah. So I didn't also. I'm trying to keep away until the end from being Bayesian or non-Bayesian. That is, mixtures are useful whether you're a frequentist or not. But the Bayesians are very, very practiced in mixtures because they're the conjugate families very often. They go with each other. So.
You're going to tell us why that is?
Yes, if you like, maybe. So the beta binomial mixture is a very natural one, and that has a nice application that actually Nico Veronco, who was here last week, has done, but it's used a lot. And the idea there is to say, okay, so you take independent binomials, and you know the number of trials, so n is fixed, it's not unknown, but p is unknown. So you have a probability of success in your 0 and 1s. So you see a sequence of 0s and 1s. Okay. Here, this is the writing out the number of success. Now, if it's IID, then it's equivalent to just looking at the number of successes in your formula. But you might have something slightly different, and we'll talk about that. But suppose that you wanted to generate just IID, well, independent binomials, but you're going to use different p's. So you need a distribution, and this distribution has to be over 0, 1. And the first distribution you might use is to say the uniform. Okay, so that's distribution is to say between 0 and 1, everything is equally likely, and it's flat distribution, and I draw one at random. So I draw a number between 0 and 1, and then I draw from the binomial a certain number, and so on. Now, if you have more information about what you're doing, you might want to use a different beta distribution, and this general form of the distribution, which is a little bit equivalent to the gamma for general parameter, but for on 0, 1 is the beta distribution, and here it has two parameters, A and B, and some of the distributions, if you have A and B which are smaller than 1, you get something like this. You could get something like that between 0 and 1. Or if you have, you can have something which is asymmetric. You can have something which is like that. So again, it's between 0 and 1. Okay. So that all depends on. So here I'm generating a lot. I put alpha is 5 and beta is 35. And if I generate 50,000, and this is what I get for the beta. Sorry, it's that. That's the beta. So I'm generating all the parameters at random. I call them theta. They're the parameters that I'm generating for my binomial. And this is what I get. So it's something like the distribution I show over there. Okay, so then for each of those, I take some, and I do a binomial with that probability. So here I have a probability, maybe I chose this one, 0.3, and I flip a coin with probability of success 0.3, and so on. So that's what a beta binomial mixture is, and this is what it looks like. This is the marginal. So here, how many did I do? I can't remember. Sorry, I can't remember. 300 trials. So when I did 300, I never even got a half. And this is what the distribution, but that's the mixture. And so if you got something that looked like that, then you can think of a binomial beta. Now, in many of these cases, it's useful to think about Earn models. And the beta binomial is a good example of an Earn model. And all of these Earn models are, there's a main form of them. So Polya's Earn. And the way I like to explain about it is think about the following process. So you go downtown, marketplace, so on, and you don't know anything. It's 11:30 and you want to have lunch, okay? And you don't know anything, and so you look in all the restaurants, and one of them has several people in it, and all the others are empty. So you go in the one which has several people in it because they probably know something. They're locals, it's probably the food's decent, okay? That's even more so if you go at 12:30 and most of them have a few people, but one of them's empty, you're not going to go into that one. So that's like Polya's Earn. And what happens is if you go in, if all the restaurants started off at 0 and you go in, then you choose this restaurant at random because there's nobody in any of them, so you use a uniform. But then once you're in there, the next person who comes in is more likely, very slightly more likely, to go into yours, and so on. So it's proportional, the probability will be proportional to the number of people plus 1. So here you start off with 1 over k, and here there's k plus 1, and so it's 2 over k plus 1. Okay, so that's a Polya Earn. And the beta binomial can be seen, the marginal distribution, as a process like that. Yeah.
So bacteria multiply.
What?
Bacteria multiply.
Bacteria multiply, yes. So
one would like to model one would like to model this in some way as once the bacteria arrive and then they multiply, and then the more they multiply, the more they multiply. So is this the kind of model we can use for that?
yeah, Chris.
This is actually the neutral model, in some sense. In the sense that this, if you had red and black bacteria, and they had neutral population dynamics, and you took a sample from that community, it would be a beta binomial. So,
But
there is a relationship to bacteria in that sense, or multiplication of bacteria. I think that's true.
But you're trying to tell me that they multiply, so you don't want to do adding. Is that the thing? I mean,
I'm not sure.
okay, we can think about it, but that's so in this case, the parameter of the beta, is the A. It's the number that you add It's slightly more complicated model than here. And so when you observe a red ball, you pull out the red ball from the urn and then you put it back with as many red balls as is A. So you could put it back with 10 red balls or and so on. So, but you end up with the same marginal. That's an urn model, which is sometimes useful for people to think about. So this very nice application, sorry, my math jacks, I had a little bit of problem with the math jacks in the middle of my page. So here we have beta binomial, which was used in the very nice bioconductor package by Nico, and it's called Deep SNV, and it's for single nucleotide variants, and it's looking at an enrichment of the binomial model where you're going to put in information in the P's. They're going to be different according to, so it's counts and according to the position and the nucleotide. It's a very good example if you're looking at looking for a realistic mixture model, because this one works very well. And so this is the beta binomial that he uses.
So they don't have a...
What?
So do they have a... In their case, they have a mechanistic interpretation of the mixture? Yeah.
They don't care. They just say it's variable. And they use the parameters that they estimate on the variability to condition, and then to decide whether it's a variant or not. So whether it belongs to the overall distribution, which is an over-dispersed binomial. Because what happens is, if you just take a Poisson, or if you just take a binomial, and you don't account for the extra sources of error, your variance estimates are too narrow. And that means that when some new thing comes up, your hypothesis test says, this is different. And it's only different because you have made some narrow assumption about your distribution, whatever it is. Okay? You've modeled it without the over-dispersion, and you've seen something here, and you say it's significantly different. It's different. But that's really because your model hasn't accounted for all the sources of variability of this over-dispersion, and then it might be that your true distribution is much flatter, and that really your thing is here, and you shouldn't. So these models, these over-dispersed models, allow to put in extra variability and not say everybody comes from the same parameter. I see a lot of puzzled looks, so I just tried to be helpful, and it was just completely... it's just saying the motivation for this has a lot to do with getting rid of a lot of false positives. Yeah.
This better distribution over binomials, and they estimate that, and then they say there's binomial distributions that explain the NAR model.
So if you just had an ordinary binomial, something like that, it would be narrower. And the beta binomial will have the effect of spreading out. It's over-dispersed. So the marginals, at the end, you get less false positives, because you've accounted for all the sources of error, the extra sources of error. Because in some sense, when you're saying, everybody, all the positions and all the nucleotides, everything is behaving in the same way. So you're saying there's just one parameter, okay? And in this model, you're saying there's lots of things in the parameter, and I'm going to put them all in, and it does a better job.
That's a sort of general reason why you might want to do mixtures.
Yes. But yes, it's a general reason. I mean, it's a reason why people did it a lot for RNA-seq. We do it a lot for RNA-seq, and we do it a lot for places where, although you can't exactly say what the error is, you're borrowing strength by saying, well, there's this overreaching mixing distribution, and I don't have... It's like what people did in analysis of variance when they do random effects models. There's this extra... So and so the results that he gets here that have to do with the actual the nucleotide is colored, and these are the ones that come out significant, and this is the rest of the in the test. But this, in some sense, was able to find all of these significant ones without getting all the noise, and it's a much better test. It's a very nice example, so I recommended the vignette of the deep S&V package. It's a good example of using the beta binomial. So that was my biological examples. Let me go back a few more simulation examples. Here, I was happy I found this in the MBE. And so this is typically, now I have a trained eye, so I see these, you see a histogram like this, and I know already that these promoter lengths have a Laplace distribution. And so it tells you that originally their components are normal, but they don't all have the same variance. And you can just see it. This would be a very good fit. What would we use it for? Well, it's very useful to be able to generate data the way I was talking about doing power simulations yesterday. If you want to generate data under null hypotheses, because you want to test your data to see if it's significantly different or not, we do what we call the parametric bootstrap. So that method means that you generate a lot of data according to a realistic noise model, but where there's no effect. But you want to have something which will have the same variability as your true data. So a parametric bootstrap is like a Monte Carlo with a model with mixture models. So that's one of the reasons why making a model for the data can be very useful, because you can do the test and you generate a lot of data with the same error distribution and the same components, and then you can look at where your observed data is compared to your actual data. So of course, if you generate, if you had this kind of mixture distribution, and if it's at the end, you'll be able to say it's significant, otherwise not. But it's very useful for this parametric bootstrap. And this was an example of where I used it. So this was this is microarrays on T cells, but the cells have been sorted, so there's no heterogeneity in the cells. They're all naive cells. Unfortunately, there is a lot of heterogeneity in the variances, and so you get something like this, which is not at all normal. So, but you can get the right distribution for the residuals and do simulations.
Susan,
Yes.
For a parametric bootstrap, how do you choose a test statistic?
How do I choose the test statistic? It depends what you're looking at. So it depends what you're generating.
In some cases, I've done it, and for some test statistics, I will find that it doesn't look different, and for some it does. And you sort of then wonder, is the data different from the model?
Yeah, so of course, the parametric bootstrap will only work if your model is right. You can't test the model with it.
Point. Yeah, I mean, you're trying to test the model, right?
No, you're not trying to test the model. You're trying to test, say, a difference. I mean, a treatment effect or something like that. So the null hypothesis would be, the way I do it is the null hypothesis would be you put the treatment effect at 0 and you generate, all the different, whatever it is, I, J, K, L, and then you have whatever effects that you put in, plus your noise model, so that the overall distribution, has the right distribution compared to what your distribution is, and then your null, this is the way I do the bootstrap, you generate data with the null here, the treatment equals 0, and then you look at whether the values you get on your data are extreme or not. I don't know what test statistic, I mean, it's just looking at the overall median or...
Okay, no, I mean, I see what you mean. Sometimes I'm generating quite complex types of data, and then it's actually, I guess the question I'm asking is how do you compare one bit of data to another? I mean...
Yeah, but I think that the first step would be to do, once you've chosen whatever your choice is, something like this, you're going to use the median, or you're going to use, a quantile.
Yeah, no, I mean, my data is much more, I'm generating data with structure, I guess.
Yes.
But don't worry about that.
Well, we can talk about that. I mean, but the thing is, usually what you do is you have to prove that your statistics captures a difference without capturing too much of a difference, so you have to do simulation studies, right, to begin with, on the fake data before you put the real data in.
The question of statistic really comes down to, is that statistic going to be able to, is it going to be sensitive to the thing you're looking for?
Yeah.
And so some things that we say are more powerful than others. And, if you're looking for a difference in means, and you're going to compute something which really doesn't depend on the difference in means, then you won't see a difference, obviously. I don't know if there's any, if you've got a simple situation, you can work out, the uniformity.
Yeah, but I think that mostly, when you bootstrap, you have to tailor. Yeah, there's sort of an art in trying to find very often the difference. So in this kind of situation, it would be, the y observed and the y theoretical, I don't know. And then you have some kind of estimate of the standard deviation of the y, for instance. So this is a studentized statistic. And y, when you bootstrap, even if your data isn't normal, what you're aiming for, a good statistic is a statistic which is pivotal. So it's a statistic which doesn't depend on unknown parameters. So the t statistic is chosen because it has a distribution which just depends on number of degrees of freedom, but it doesn't depend on the mean. So a good statistic is a statistic whose distribution won't depend on unknown things. And there's lots of literature on studentizing and doing double bootstrap, pre-pivoting for making the bootstrap statistic pivotal. But yeah.
I think we're getting very statistical now.
We're getting very statistical. Sorry, yeah. Yeah.
Excuse me.
Okay. So this is all the data that we had on the Laplace and the example that we did. This is a QQ plot. I did want to show you a QQ plot just because when you're fitting all these models, it's pretty important not to look at histograms because histograms all look the same. That is, very often when you look at histograms, they go up and they come down. And mostly people will say, well, that's bell-shaped, and so it's normal. And very often you have data which actually isn't normal at all. The normal might be much. And this really matters because out in the tails you really care. And so you're much better off making a QQ plot where you plot the probability, the quantiles of the theoretical and the observed. And you want to get a straight line if your fit is good. So fitting models So here you see there's not a perfect fit on the left here, but it's a pretty good fit for the most of the rest of the, it's quite a good fit. It's a much better fit than the normal. So this is the asymmetric plus, which is another, and again, this is a mixture, it's a multivariate mixture where you want to take into account the covariance structure at the same time. So you want to generate multivariate normals, but with a covariance matrix. And we know how to do that through the Cholesky decomposition. And it's for the kind of bootstrap thing. Okay, it's too much statistics, all right. Okay. So, where do they come from? Well, there are these differing technologies and differing bindings and PCR bias and all these technology problems. And you get this problem that the means and variances depend on each other. And you have to fix that. That is, in order to test anything, and this is a good example of what has to happen, when you're testing, you don't want to have something which depends on the standard deviation, and having a different standard deviation at different parts of your zones where you're looking is going to make your t-statistics and everything work badly. So if you have the variance in the mean, well, the variance depending on the mean, you have to do what's called variance stabilizing, and I think that the best example is for the Poisson. And I'll talk about that after. So we talked about, just to stop and say these are the common ones that come up the most, the mixture of normals, beta binomial mixtures. So I showed you an example where you have a distribution, a beta distribution for the p. You have the gamma Poisson, the gamma exponential, and then the Dirichlet multinomial, which comes up a lot in the Bayesian framework, especially for doing various kinds of categorical examples. And if you don't know anything about the Bayesian framework, it's a shame, because now we have modern computers, it's really useful. I wrote a paper with Percy Diaconis about the birthday problem, so it might be a good introduction to the Bayesian framework. Should I say it? Is anybody interested in the... Okay. So the birthday problem, who knows about the birthday problem? Anybody taught introductory probability?
I've forgotten what it is.
Okay. So the birthday problem is, how many people do you have to have in the room to have a 50-50 chance that two people have the same birthday? And if you think very, very quickly about it, you answer 180. Okay, so that's the first off-the-cuff, thinking about it. Now, if you think a bit more carefully about it, then you can do this computation, which we do in introductory probability classes, and because the number of comparisons is actually very large, it's the number of people in the room choose 2, then you realize that you only need about 23 people in the room to have a 50-50 chance. And with Percy, we have taught a lot of probability classes, and what we realized is when we teach students, usually freshmen, but sophomores, we were getting we were getting much better than 50-50 on classes of around 20 students. And so the question is why? And how could you use some prior information on that? So for that, then you can say, okay, I'm going to think about my probabilities along the year, not as all fixed 1 out of 365, the way we do it traditionally. So why wouldn't you do it? So you say P1, that's the traditional P100 and 365 is 1 out of 365. And you could say, well, actually, so I know something. So I know something about the people in the class. So say they're all sophomores. They probably mostly born the same year. Okay? So they're born the same year, then the weekday and weekends, all fixed on the, and in the States,
There's a lot of cesareans.
yes, in the States, more than 50% of babies are born by cesareans. Cesareans don't happen on weekends. And if you go into labor on a Friday afternoon, the doctors have a large choice of drugs to give you so that you won't have the baby over the weekend. So it's definitely not random across the weekend, weekday pattern. And if you look at the data, it's sort of, so it's like this. If you look at the probabilities, it's sort of higher. They hurry things up a little bit on Fridays, and then it goes down for 2 days. And then all these people who waited, and okay, something like that. So this is Saturday, Sunday, Monday, Tuesday goes back down, and so on. And so you have this, okay, you have this pattern, and what you want to do is you want to say, okay, I'm going to put this in, and we put it in the form of a Dirichlet, where you have different parameters on weekends that you do on weekdays. So you have a mixture. And so then you can compute what the chances are, and in fact with that Dirichlet in that paper we proved that you only need 16 people in a room in order to have a 50-50 chance if they're all born in the same year. And that you have...
Based on American.
Oh yeah.
Earth facts.
Yeah, but you have all that information. You look at the room. How is it in the UK? Do you know that number? Is it much less?
For cesareans, it's much less than
That's funny. Okay. But they use the drugs, don't they?
that. Yeah.
I'm sure in Europe they use the drugs that.
Yeah, well, I think the difference would be in America they do it for convenience. Because I remember we had one kid in America, one in Germany.
Yeah.
And
No, it's not a convenience.
I'm
It's
working
not.
on this day and that day. So it'd be good if you had the baby on one of those days.
Yes.
And the other day, my colleague would have to do it. So she
Yeah.
was actually trying to get my wife to take
Not only that.
inducing drugs just for her convenience, not.
No, but I don't think it's convenience. I think that in the U.S. it's the lawyers, because if it goes badly, and you then you sue, and doing cesarean sections is very, very straightforward. It's like this operation, and
This was just a drug to induce on a certain day.
to induce. I
Yeah,
see.
not
Drugs to induce. I
just
see. I
so
see.
because that's the day that she would be in the hospital.
Right.
So it'd be
Right.
more convenient for
No,
her.
no, no. I agree. I mean, I just say it's a real phenomenon in the U.S. So we were able to use that, and then you can do the probability and use that you can enrich the model with information. So, to be honest, I did that in a Bayesian way. That is, we put in prior, and we put a Dirichlet prior on the p's, and this Dirichlet prior had different numbers for the days of the week, and all through and that's how we did the computation. And nowadays with MCMC, you can put in these kinds of things.
What's your actual data?
What's the actual? The only data is records of dates on births on Monday, Tuesday, Wednesday. That's the only thing.
So you're going to fit the... Oh, okay.
That's the only data, and we put that in as a Dirichlet.
Okay. But you could also... I mean, you could use the raw counts to generate a... You can count, just based on how many you have born on each day, you can... Well, so there's some...
I mean, you can't cheat, because then you could cheat, because if you knew, lots of people born on Thursday, then you could...
I presume you didn't have access to the national...
No, we just used some numbers that we found on the internet.
I mean, if they were small numbers, if they were sort of thousands and thousands, you wouldn't need the Dirichlet. You would just say,
Yeah.
let me just point estimate these these probabilities.
Yeah, no, but we didn't do we didn't do point estimate. We did a prior. We did a mixture,
Which
a
would
Dirichlet.
be important if your sample wasn't so large
Yeah.
that you could be so circumspect.
Right,
Yeah, I mean, if you actually had the data about how many people were born on each day,
right.
Even that wouldn't be precise because you're trying to come up with something that's not what happened last year across the whole USA is not going to be precisely the same as what happened here.
Well, things do change. You want to have how things were about 20 years ago, right?
Okay.
Not this year. Anyway, I'm just giving you an example. Okay, so I said that I'd do a little bit about variance stabilization, and let's see if I do the Poisson. Do I talk about the Poisson? I don't really want to know. So that's the justification of why we did what the variance stabilization gave us in the case of the Poisson gamma. But just to say what Poisson stabilization is, variance stabilization is for the Poisson, it's only you try to find a transformation g of your random variable such that the variance of g of x is approximately constant. Okay? And for the Poisson, the transformation, if you take the square root of x, then the variance is approximately going to be 2. So the variance will be constant. So if you have the variance which is constant, which is ideal, which then this transformation has saved you from this problem of having different areas. Very often you have, I showed you plots the other day where you had the mean and the variance, and as the mean increased, you had this, the variances were going up, and so they were increasing. So variance is a function of the mean. And this is something that you don't want. So we know how to do these analytically, and I'm not going to really show you how to do that. But basically it's called the delta method. Yeah?
So for this last, for the birthday problem, can you just say just the individual steps more in detail? So, so you have the Dirichlet distribution, which is how I estimate, and the birthday.
But you have the marginals, but then you have to find out what is the family of distributions underlying, so that you know what the transformation should be. Is that the question? Right.
the mixture is that given someone is born on a Monday,
So the multinomials, they have the days of the year, or every day is.
The multinomials are the probabilities are, it's a multinomial with P1, P2, P365, and then you take a Dirichlet and suppose that, this is Monday. So that would be Monday, Monday has its own day, and then Tuesday.
you're saying that the 365 are sampled from 7.
But here, the sample size, you look at the prior data just to say, oh, it's 70%, the ratio of the alpha to beta, that the gamma one is the most important. Let me finish. So Wednesday, Thursday, Friday, maybe, and then you have this delta delta. So what you know is that these numbers have to be smaller by about 70% of the betas. So you put in some numbers, and that just depends on the strength with which you believe the prior, but it doesn't have any effect. So you put in some numbers here. You might put in, it's something like, I can't remember. So say 6, 5, 5, 5, 5, 2, 2, 6, 5, something like that. That's your Dirichlet. And you generate from that every time the p's. Okay? So you generate a p from that Dirichlet. And then you, for each of the, okay? And that's what gives you, and then you look at, you choose a person born one of those days, according to that. And then you do it again. Okay? Does that make sense? So that's how you do it.
So you sample from this Dirichlet of P.
But it's this hierarchical model in some sense. This is the Dirichlet from which you generate then the p's. It's like in the beta binomial. It's the same. And then from this, you generate a birth.
Yes.
Yes, okay, okay. I wanted to show you some applications. The negative binomial, this is one of Joey's examples in the vignette of the philosec implementing the negative binomial, and it gives you some of the code to actually do it. So we use the dsec2, which models the negative binomial. So behind it you have, in fact, the estimates of the variances and the different component factors. And I'm not going to do any of that. It's just to say, we know how to do it. So here you had the fold change according to that. And you see quite a big fold change here, the log2 fold change, according to the different phyla. And again, it gives you better power if you're able to model out the noise, the over-dispersion noise, which is due to technical reasons. What's left over, the treatment effect, you have a better estimate, so you have higher power. So that's just an example, and I've put a link in the slides to it, so you can do that.
In that case, you
Yeah.
actually modeled this with a negative
Yes,
binomial.
yes.
Could
Well, you model the parameters in the negative binomial. Yes, we have to estimate them by a robust method. We didn't use maximum.
So wait, this is frequencies, first of all.
Yes, this is frequentist.
Frequencies.
Frequencies. What frequencies?
So what are you modelling here, actually?
Counts, never frequencies.
Yeah, counts. Okay.
Yes,
Good point.
but we can't do proportions because we need to do all of this. We need number of reads.
So my question is this: that if you believed your data were negative binomially distributed,
Yes.
and you could go forwards with a sort of maximum likelihood approach with that, could you instead just do this square root transformation and do a look at it some other way?
Yes, but there are things we do that. We don't do the square root actually, we do some other transformation, but that's not enough. We need to estimate the parameters as well, because you want to know what the variances are. Because the variance of the noise tells you something also about the variance between the, so you need to use it.
So are you actually trying to get the underlying components of the mixture, estimate the underlying components of the mixture?
The number of components.
No, not the number, but get at the underlying components.
Be able to say what they come from. Depends how the experiment is run. That is, that's where the design of the experiment comes in, because if the design is well done, that is, if you have lots of replicants and you have a block and so on, you can get at all the pieces. But often you have confounding, so we lose it. I just wanted to go back to that last question I said that I would ask before we get to the end. Come on. Now I've lost my talk.
Yeah.
Okay. So I wanted to say just mathematically why do these, so they come up a lot, and I wanted to say a few sentences about why we know that the mixtures are the right models. So even if your data isn't independent, we very often have what we call exchangeability. So that says that if you have, for any n, if you have the distribution of x1, the joint distribution there is equal to the joint distribution of any permutation, that is, you can move them around, then we say that it's exchangeable. Now, if it's only true for, if you have only a finite version, there are finite versions of the theorem, but originally it was for any string you always had to have this exchangeability or permutability. Now, of course, independence is a trivial case because if you look at the joint distribution in the case of independence, that's a product here. And the product is commutative, so you can permute these around whatever you like. That doesn't matter. The converse is not true. That is, that you don't have that exchangeability gives you independence, but independence does give you exchangeability. So the idea here is to be able to say, for instance, in a binary example, that this string here would have the same probability as that string. It doesn't matter what order they came in. And so if you're interested, and I'm not going to do all the theory, but this is a very nice lecture prepared from somebody from the other place. Because we got lectures on Saturday about the other place, so and so there's a definition of exchangeable, and then, for instance, he gives the example in the polar urn. You can prove, why it's exchangeable, although the probabilities are going to depend on how you drew. In fact, in the overall probabilities, the numerators permute around, but in the product you get the same thing. So the probability doesn't matter. But they're not independent. That is, a sequence from a polar urn is not going to be independent. But overall it's exchangeable. And then there's a Gaussian example. If you look at a multivariate Gaussian centered and such that all the variables have correlation rho, and it has to be positive definite, then you can look at the vectors, and they're exchangeable, although they're not independent. Okay. So what does De Finetti say? If you have exchangeability, and he did it just for, suppose that you're doing Bernoulli and zeros and ones, and that they're exchangeable. Then he says that there's always a mixing measure which exists such that your probability is equal to, it's like a sum here, but it's an infinite sum for the mixing measures on the thetas. So in some sense it justifies this binomial beta, because that's what this is. It's going to give you, and you can get at many mixtures, and this extends to many different cases. He just did it for zeros and ones, but it extends to a lot of different situations. And so that's why I say, if you want to look at this further, there are many further developments mathematically, but I think it's very interesting to know that there's some deeper fact, underlying fact about the justification of why these mixtures are there. And whether or not you think about it as a Bayesian, I'm not in the business of doing religious conversion. I like to use priors when I have prior information, like the case of the birthdays, but I'm pretty pragmatic about that. You can also, if you want to look at, so here this is the case of Polier's urn and how it was studied. There's a Gaussian example. There are other, I'm going to tell you. So there's a finite version, just to say that if you had a smaller sequence than an infinite sequence and it's k exchangeable and you can extend it, that also gives you the same type of theorem up to approximation. And the approximation is of order 1 over n, so it's okay. So basically the take-home message is that the De Finetti's theorem very often gives you a way of considering things as mixtures. And for instance, if you start off with saying that you have a little bit of prior information about what you're doing, so just to take a little example, if you spin a coin on a table, in particular a US penny, and then you bang on the table, it'll come up not 50-50. It'll come up probably 80-20, but it depends on the coin. So if you have a coin, which you know is a 1963 penny, blah, 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 and you know your coin and you've done your homework, you can do bar bets with it. Right? Because you can say, oh, I bet you it'll come up, but you know that it's... So in order to... That's the prior that you would put on. The prior would be that you don't know what your particular penny does, but the prior you'd put on is that it's unfair. So you'd have a beta which would look something like this, which is a beta half a half. So it's higher probability at the ends. So you have a situation where you know ahead of time that it's unfair, but you don't know where. But as soon as you've observed a couple of tries, then it becomes, then you start to have something which is nice and you'll know where it is. So the families, the beta binomial, if you take a prior on the parameter, you say that P is a beta. Then after you've seen the data, say AB, if I saw, say, I run a trial and I know what my trial number was, it was N, and I saw X successes, then the posterior, the distribution of P after seeing that, so the posterior of P is a beta, and the with n minus x plus a, and then x plus b. So you add on the number of successes here and the number of failures here, and n, of course, is very important. It tells you something. And in some sense, you can think about the parameters that you have in beta. The way I think about it, I think about it saying how much previous data is it equivalent to. So that's how we, use it in the Bayesian setting. And De Finetti's theorem sort of justifies why we can do that. Okay, I think that's as much as I... So you want to talk about your mixtures?
I'm not sure, because I haven't. I was
it.
confused by our conversation, so I didn't do it.
No, it's fine. I'm giving you a hard time.
So,
yes,
yeah.
but you can give me a hard time. You can ask me questions. It's not.
Well, yeah. So, maybe what I do want to say is that the kind of mixture modelling I was thinking about is where you are actually interested in deconvolving what the elements are.
Yes.
Then what do you call compositional data?
So
Yes.
you have this.
Yes.
You have this distribution which you know is a mix
Of normals or whatever. Right.
components are, and you actually want to find out
Right.
what the components are. So when, for example, if you're going to use k-mers to look at composition of communities, okay, so each species that in there generates a distribution of k-mers in each particular read.
Mm-hmm.
Okay, and then in some sense the problem is given your overall distribution of k-mers, it's a mix. Each breed comes from one organism, and that organism is a. So you sort of want to know the middle layer of the mix.
Yes. So the way the statisticians think about that is we talk in terms of data augmentation. And data augmentation is to say that you observe some data and there's something missing with it, which is the class that it belonged to. And then you use the standard method is expectation maximization. So use the EM algorithm. And it's slightly like what happens, it has a lot of things that go with what happens in hidden Markov models, for instance. Because it's sort of circular. You start off by an initial guess, and you compute the parameters for your model. Okay, so you start by assigning people at random to a group. Then you compute the means of all the groups, and then you compute the likelihood of your data. And then you try to change some of the assignments to maximize this, right? And then you change some of the assignments, and then you compute the averages again. So it's circular. You start off at some lousy guess, and you just try and improve it. But you go around in circles. And that's called the expectation maximization algorithm. And that's how people do a lot of these data augmentation problems, where you say you have a missing. Is that right, Wally? I mean, you know about that.
That's a fair way to
So
put
you
it.
can have the missing layer which tells you how things are distributed.
Yes.
Yeah.
But there's a complication in it, in that it supposes that otherwise you have to add a layer if you don't know how many clusters there are.
And these things are never guaranteed to get you to the optimum. It can be very,
Yes.
depending on where you start from.
But I mean, it's still what statisticians do a lot. They do this data augmentation.
Easier to implement that usually than a Markov chain Monte Carlo. So
Right.
That's the other way to do it. That's the standard, and
Yes.
everybody seems to do that.
Yeah, okay.
What people are doing MCMC nowadays with
Yeah.
the Dirichlet process.
But the MCMC allows you to get a posterior distribution and gets a much more refined type of model. I mean, I'm just saying, the EM is what people do when they do mixtures of normals. If you said, your data, just know how to do it.
Effectively, I did regularize the with my variational base.
Mm-hmm. Right.
You do these starts at with different settings, so you find, and then you pick the best of all to avoid the slow local versus global optimum.
That's what people do, I
Yeah.
think. I mean, I think it's especially difficult with mixtures because there's always a chance that you maybe put another component in and it would change things quite a bit. They can be quite sensitive. So you can get different solutions depending on where you start. And there's various sorts of techniques that will kind of try and fudge a whole bunch of different solutions. So it's not perfect, but I think that it's partly a sort of very, to some extent ill-defined problem, because if you're saying how many clusters are there or how many groups are there, well, it may be that some of these groups aren't even represented in your data. They're very rare, and so in a sense you can't really find out. If there are clusters there which are so rare that they didn't actually turn up in your sample, you can't say that they don't exist. All you might be able to say is that they don't exist in my sample. So it can be, it's always a very delicate inference business. But I think people take a pragmatic approach usually. And that's good. Then it looks very confused.
I'm sorry, I didn't give the right talk. I actually have a talk about the EM algorithm, but that's not what I understood.
Well,
I can sit down and we can talk about the EM algorithm.
no, I don't like it.
I mean, what we could do is have this as a topic for discussion in the modelling
Yes.
group. We could have another sort of chat where we focus more on compositional models.
Yes.
Yeah. I mean, I've done quite a lot of stuff.
Yeah, I knew that. That's why I didn't want to,
And in particular, I mean, Wally was talking about the question of how do you determine how many mixtures are present. There's quite a popular way to do that at the moment through something called the Dirichlet process, where you effectively have an unbounded possible number of types present, and then you actually have a posterior over the number of types in effect. So your model includes all possible. I mean, which sounds great, but actually in practice it's not as great as you think it is. Because in practice, then there is a parameter that controls sort of how likely you are to add a new type. And almost definitely your number of types depends on what you set for that parameter. And then, I mean, there are then ways to sample that parameter as well.
But they have all the Bayesian non-parametric methods with all these restaurant processes.
Yeah, I guess what I'm getting at is that there is Bayesian non-parametrics, but there is a parameter, which is the rate of formation of new tables.
Right. No, I understand. But you have the Chinese restaurant process, the Indian buffet process. They have.
And why are all these given sort of?
Jim Pittman is responsible, I think, for the first naming of the Chinese restaurant process, because in Berkeley the probability seminar historically always used to be in the Great China, and they have round tables, and people would arrive at random, and you'd go and sit next to somebody, and on a round table there's no limit really in how many people sitting around, or you could choose to open a new table, and then. And so that's why he called it the Chinese restaurant process. And then they wanted to add complexity, and I think it was Zubini, but Zubin Garamandi, I think he wanted to add the fact that when you choose your food, you could go on choosing different.
So the Indian buffet process is an elaboration of the Chinese.
Yeah, they're related, right. But
there's also the Chinese restaurant.
It's all very, very relevant to the type of data that we're looking at, because it's ways of making partitions of the data. So if you worry about not what's there, what the names are, but just the distribution of how the counts are distributed, that is, you could try and find the right process which explains your counts, your patterns. And the champion of that, and that's a paper I haven't mentioned because I didn't go into that, but it's a very, very good paper, very interesting, and it's by John Kingman, and its uses of exchangeability. And he has it's about partitions, random partitions, and he has what he calls the paint box process, and how you can use exchangeability to try and see, how the distribution of the frequencies of the different species can tell you how many species there are, for instance. That's a good Turing problem, but it goes further than that. But that's a nice paper.
John Kingman.
It's the same Kingman as the coalescent.
Yes, and he was a former director of
Yes,
this institute.
that's true.
Among his many.
And David Aldous is our advisor. So, right. So, okay, that's enough, I think.
Thank you very much.
Okay.